Hello, here in this video we're going to look at probability part 3, and it's going to deal with something called conditional probability. The probability that event B will occur given that event A has already occurred is called conditional probability. The notation looks like this. We have the probability, right, that's what that P in the parentheses stands for. We have B, a vertical line, and then A, which is red, the probability of event B given event A. Now there's a couple different ways of doing this. Contingency charts, or a two-way frequency table, is a table that contains data from two different categories. This and tree diagrams, which you can just draw out and make pictures, can help solve conditional probability. The table shows the gender and type of school in 2005, and it's asking when you pick a student at random. And then it's going to have some questions for us. It's going to say, what's the probability that the student is female given that they are in graduate school? So this isn't asking us to just take females in graduate school and divide it by the total number of students, because we're looking for when graduate school has already happened. So instead, we're just going to be looking at this column in general. So when we're looking for the probability that someone is female, given that we're already looking at graduate school students, it's going to be the female amount, but then divided by both of these together to get the sample space, because we're looking at graduate school only. And when we do that and we put those two amounts together, what we get is 3,303. So the probability that we'd pick a female student, given that we're looking at graduate school, is 59%. Right, and this is different than just saying what percent of students are female graduates, because that would be the 1,954 divided by all those students together. But conditional probability tells us that we're already looking at a specific set. So the next one is probability male in a 4-year college. So we're not looking at the whole chart. We need to look specifically at 4-year college and then the male. So it'll be 4,324 divided by both of these put together. So 4,324 plus 5,517. And then when we divide those, we would get to see the probability that the student is a male, given that we're looking at 4-year college. And that's going to be, if you round up, 44%. Now, for this next one is not conditional probability because we don't see the line. This one just wants to know probability that we're looking for a female, that we'd get a female if we drew one out. So that's when we're going to use the entire chart. Conditional probability is where you're looking at subsets of data within the chart, but regular probability is just what you're looking for divided by everything. So if I put all three of those numbers together, we get that there's 9,933 total females, and we need to divide it by all 6 of these numbers, which is 1,472. And when we divide that out, we'd see just the probability that we got a female in general, which is 56%. And then we could do one more. 2-year college, given that we're looking at females. So this time, we're looking at this set of data. So here's all the females. And then we need to backtrack it to where we're looking at a 2-year college. So we already know that females is the set that we're looking at. The 2-year college is just this one right here. So we'll have 2,462 divided by, and then the total number of females added together, which was 9,933. And when we divide those, we get 24%. So we know that 24% of the females attended the 2-year college. So what conditional probability allows us to do with tables is look at specific sets within other sets of data. Meanwhile, regular probability is going to use the overall sample size where it's all the data put together. Conditional probability allows us to be a little bit more specific when we're looking at a certain parameter, which in this case was females, in this case, 4-year college, and in this case, graduate school. Now, you won't always have a chart. Sometimes you'll just be given probabilities, and this is going to be the formula to help us determine. If A and B are dependent events, right, and remember that dependent means one impacts the other, then the conditional probability of event B occurring, given that A has already occurred, is this right here. You'll see that same line, which is the conditional probability sign. We're going to need the probability that A and B happened, and then divide that by the probability of A. So we're going to attempt one here. It says, at a restaurant, 25% of customers order chili. If 4% of customers order chili and a baked potato, find the probability that someone who orders chili also orders a baked potato. This is conditional probability because we're looking to see if somebody ordered a baked potato when they've already ordered chili. And so to do this formula, we're going to need to find the probability that someone ordered chili and a baked potato, and then divide that by the probability that someone just ordered chili all on their own. And coming up with the proof for this formula can be complicated. Probability formulas kind of are. So you'll want to just lean on this and input your numbers. So for us, the probability that someone ordered chili and a baked potato was given to us. It was 4%, so that's 0.04. The probability that someone got chili is 25%. And when we divide both of those together, we get 0.16, which tells us there's a 16% chance that someone ordered a baked potato, given that they've already ordered chili. Coming up with this on your own without the formula can be very difficult unless you draw out a tree diagram, which is where you just list out all the possible scenarios. But this formula can save time and energy when trying to calculate conditional probability. Binomial probability is one of my favorites, and we're going to see that moving on. Binomial probability refers to the probability of exactly k successes on n repeated trials in an experiment which has 2 possible outcomes. So it's important that we know that this formula only works when there's 2 outcomes, such as, make or miss. But you can do it such as rolling a dice, even though there's 6 sides, because you can set it up to where you have one number that you want, and then there's other numbers that you don't want. That's still 2 options, a happy success or a sad defeat. If the probability of success on an individual trial is p, then the binomial probability is this. So what we're going to have is n choose k, where c is that choose function, and we're going to multiply it by the probability of success, all right, raised up to the x, and then the other part of the probability, and this will make more sense, the 1 minus p coming up, to the y. And here's what these are. N is total number of trials. K is the number of successes. And then X is amount of successes. So these are really the same thing. I could have set these up to be the same thing. And Y is the amount of failures. So this formula, even though it may look complicated, is fast and easy. It's one of my favorite formulas to use in the real world. I mostly use it when I lose at something and I want to complain about how unlikely something was to have occurred. And here's a couple examples. Let's say that you make free throws 70% of the time. and your friend challenges you to make 10 out of 12 shots. We could calculate what the probability is that that's going to occur. Now, we know that it's not going to be a great probability because we traditionally make, 70%, which is 7 out of 10. So making 10 out of 12 is much higher than our current rate. 10 out of 12 is 83%. Now, obviously, it can happen, but we can type in and find what's the probability just on random if we gave it to a machine, or maybe we built a machine that makes 70% of free throws. What would be the probability that we make 10 out of 12 shots? Here's what it would look like. 12 is the total number of trials. We're trying to make 10 of them. So the first part of the formula is 12 choose 10. The probability that we make them is 70%, and we're trying to make 10 of them. The probability that we miss, which is 1 minus p, right, and 1 minus 0.7 is 0.3, is 2. So we can calculate this here and figure out what's the probability that we would make 10 out of 12. And remember that choose function on your calculator comes from the math button, and then you scroll over to probability, and you'll see it. We covered that in a previous video. And if you type this in, the probability answer that you get is 16%. So if you were, playing against another team in basketball and they ended up making 10 out of 12 free throws when the team only shoots 70% as a free throw rate, you should be upset because there's only a 16% chance that, that should have happened. And that's why I like to use this formula, is really just to be petty when things don't go my way. Or it can help you feel lucky, because if you only shoot 70% of the time and then you have a really good game and you make 10 out of 12, you could look back and be like, oh, that was unlikely that would have happened. So say you're playing your favorite board game and you need to roll a 5 on the dice 4 out of the next 6 rolls. What's the odds of this happening? Well, there's 6 rolls. We're trying to get 4 different times what we want. Now, if we need to roll a 5, there's only one way for that to happen. It's 1 out of 6 chance. And we need it to happen 4 times. The other outcomes that we don't get what we want is 5 out of 6, the other 5 side on the dice, and that can happen 2 times. And we could calculate this to figure out how confident you would be that if you had to get a 5 on 4 out of the next 6 rolls, what the probability of that happening is going to be. So when you type that in on your calculator, what you get is 0.008, which if we multiply that by 100, you'll get 0.8%. So you should not feel very confident at all that if you needed to get exactly a 5 on 4 out of the next 6 rolls, it's not very likely that that's going to happen for you. And if you're having trouble believing that it would be that low, think about just trying to get a 5 on 1 roll. You don't have a very good shot. You only have 1 out of 6 chance to get it on 1 roll, which is 16%. So having to do it 4 times out of 6 chances isn't very likely. So if you were playing against somebody in a game and they needed this to happen and they got it and they got 4 out of 6 rolls, you could use this formula and tell them how upset you are because it was less than a 1% chance. Now, this binomial probability wasn't something that was in the textbook for us to cover, but I find it interesting. It's one of my favorite parts of probability because it's pretty simple to use once you've done it on a couple different things. And it's something that you can use fairly often when you're playing games that have, outcomes such as make or miss, or if you have certain outcomes you're trying to get on dice. It's very fun to use.